Good morning, all of you. So we'll start with a quote. So it is by Buddha. As a bee gathering nectar does not harm or disturb the color and fragrance of the flower, so do the wise move through the world. So we also should be in that way. That is, whatever activity we do, it should not disturb other people. It should not harm other people. It can work for your good, but it should not result in a negative way to the others. Okay, and today is the birthday of Lalande, Henry Martin Lalande. He is an American inventor and industrialist who founded Cadillac Motors. I think you might have heard about this Cadillac. And so 22nd August 1902 to build the Cadillac, the first automobile with high precision, fully interchangeable parts. Earlier in his life, he had learned precision tool making rifles during Civil War, invented the first mechanical barber's clippers, and made engines for Oldsmobiles. And when Lalande designed an improved engine, but Olds did not want to adapt it, Lalande started Cadillac to build his own brand of automobile. He eventually sold the company to Will Durant's General Motor Company during World War I. He formed a new company to manufacture aircraft engines, which after the war he produced a new automobile, the Lincoln. That company was brought by Henry Ford. So there is a lot of contribution by him in automobile industry. Okay, today we discuss about budget solvers. And before going to that, we just revise what we had done in the last class. So we have discussed about the error analysis, and we have seen what is a modified equation. So for a given finite difference equation, if you substitute the Taylor series expansions to the respective terms there, so we are going to get modified equation. And not only that, after substitution, I have to see that the time derivatives are replaced by the space derivatives. And after doing that, whatever is the largest error term, dominant error term, that decides the behavior of the solution. So we have observed that for first order accurate schemes, usually the error term contains second order derivative, and this results in dissipation error. So we have seen error analysis of upwind difference scheme, which is FDBS method. And because it is first order accurate in space, we are going to have second order derivative in the dominant error term. And we have seen there is a coefficient for second order derivative, which is called as artificial viscosity, because it behaves like viscosity, though it is in an inviscid flow. And so this brings out what is called as dissipation error or diffusion error. And then we have done the error analysis for midpoint leapfrog method, which is CTCS method and second order accurate scheme. And we have seen that the error there contains third order derivative. And so this brings out what is called as dispersion error. So we have discussed about dissipation error and dispersion error. Dissipation error, though there is an error, it smoothens wherever there is gradients of properties are there. Any oscillations, any sharp gradients, those things gets smoothened out because of its viscous behavior or diffusive behavior. But when I have dispersion error, dispersion error, though the order of accuracy is high, but the error will be sometimes so large and larger than the actual signal. So in that time, sometimes we have to apply damping. So that we have discussed later. And so we have seen nonlinear solvers. So first we have discussed about lags method. And there the nonlinearity is taken care of by lagging. And then we have discussed multi-step methods for nonlinear problems, which are Lax-Wendorf two-step method and McCormack method and beam-bombing method. And beam-bombing method, we have seen that there are large oscillations because of the dispersion error. And also we have seen FTBS explicit method and BTBS implicit method. And in this implicit method, because you will get U square there, so we'll keep it as U old value into U new value, so that it is using the concept of lagging in handling the nonlinearity. And then we have discussed about the linear damping. So in beam warming, we have seen that when the large oscillations are there, if you add a fourth order derivative to it explicitly on the right hand side, so it is called as explicit damping. And this we have seen in the result, it reduces all the oscillations and we get a good result. And sometimes we have seen that if it is an implicit scheme where we may choose, or the user may choose a large delta t, which brings out large oscillations. So at that time, the explicit damping may not be sufficient, which is of fourth order, and we have to add second order derivative on the left hand side. But at the same time, I should see that the concept of getting tridiagonal matrix should not lose. We should not lose it. So, but we have seen, because it is a second order derivative, only the coefficients of ui plus 1, ui minus 1 gets modified. That's all. We need not change any coding. We need not change any much of the formulation and all. And then we had discussed about flux corrected transport. That is where we add some damping in the predictor, and then in the corrector, we remove the damping. Okay, so this is what is called as flux corrected transport. So these are the different methods we have discussed in the last class. And okay, before going to Budget solver, I thought, okay, we will see some of the MATLAB results of parabolic and hyperbolic solvers. We will go to MATLAB. Okay, we'll see parabolic solvers. So this is a code for parabolic solver, and we have various schemes we have used here: FTCS, Gifford-Frankel, BTCS, and Crank-Nicolson schemes. And so we have asked the option for the user, so which scheme he wanted to use. And this is the problem. Actually, we have two plates, if you remember. So there is some fluid there, viscous fluid, whose kinematic viscosity nu is equal to 0.000217. It is problem from the textbook. And so delta t is taken 0.002, delta x is 0.001. And height is, it is 4 centimeters, so 0.04 meters. And number of grid points will be height by dx plus 1. So each grid distance, grid spacing is 1 mm, so 0.001. So we are going to get some 41 points. And so here diffusion number mu delta t by delta x whole square is calculated. And here we initialize only the first plate as 40 and all the others to be 0. And so new values and old values, they are initialized like that. Okay, here switch option is there. So whichever option you have taken, 1, 2, 3, 4 FTCS like that, it takes like that. So 1, which is actually FTCS explicit scheme. So you can see here, this is the formula for explicit. So d into ui plus 1 plus 1 minus 2d ui plus d ui minus 1. This is the formula we calculate for all the grid points. Okay. And if it is case 2, Gifford-Frankel. In the Gifford-Frankel, what I have to do is, first I have to use, for first iteration, FTCS method I will use. And once I have two values, then I will go for Gifford-Frankel. So this is the first iteration, FTCS for first iteration. I'm using old, U old. So using U old, I calculate U. And U and U old I use, and then I calculate U new. Okay, so this is ui n plus 1, and this is ui n minus 1, and this is ui n, like that. So this is 1 minus 2d into ui n minus 1 plus 2d into ui plus 1n and ui minus 1n by 1 plus 2d, because this side it will be there 1 plus 2d into ui n plus 1, that will come this side. So this is the way we use Gifford-Frankel method in 2 steps. First step, we calculate using FTCS, and the next you use Gifford-Frankel. And then the third one is BTCS implicit. So I will have a tridiagonal matrix, and the coefficients that we get are minus d upper and lower diagonals, and 1 plus 2d for diagonal. Okay, so like that we will calculate and your tridiagonal matrix is used here. And similarly, Crank-Nicholson, the fourth option, there the diagonal terms are minus d by 2, and 1 plus d. Okay, so these are the diagonal terms, and here also we call it tridiagonal matrix. So, and then this is for plotting. Okay, so we'll see how it executes. So if I run it, it will asking 1, 2, 3, 4 FTCS default rank or BTCS Crank-Nicholson. If I take 1, so it will solve using FTCS method. So it is coming FTCS explicit scheme. So this is the way it happens. Okay, so initially the first initial distribution is all zeros and here 40. And so the upper layers, it gets dragged. And so I will have for each time step, the final solution, steady state solution will be a straight line. Okay, so gradually with time, it is evolution, right? How the flow changes with respect to time from all zeros here. So it gradually increase, and finally you are getting a linear one. Okay, so I'm not getting how many iterations. So just I'll tell you, this is the way we get the solution for all. This is FTCS. If I put 2, then I'm going to get, sorry, something happened. Okay, 3. Yeah, I don't know, some change might have happened when I moved the cursor. So we get, this is the BTCS implicit method. And then if I put 4, I get Crank-Nicholson scheme. Like that, we can use the same formula, right? So only few, you can see the whole program with for all the 4 schemes together, it is only 80 lines. Okay, so it's a very, very small program. And so this is a parabolic solver. And if I go to hyperbolic solver, linear hyperbolic solver, okay, this I have to close it. So if I put some 6, okay. So hyperbolic solvers, again, we are using Lax, Van-Troff, Upwind, explicit, Crank-Nicholson, McCormack, BTCS, right? So all these schemes are used here. And here what we are taking a wave. Initially there is a wave and that wave moves. And that wave, sine wave, right? If you remember. So this is the wave. I equal to 50 to 110. Okay, so 0 to 50 it is 0. So 1 to 50 it is 0. And 50 to 110, this is the sign distribution it has. It is given, the function is given in the problem. 100 sine pi into I minus 50 by 60. And again 110 to 400, it is 0. So that is the way it initialized. Okay. And then we have various schemes. So this is FTBS, that is upwinding scheme. And so all the schemes, the same formula are written here. For implicit, you will have the tridiagonal called like that. Okay, so if I go for this execution, so Lax method, first one, it is asking current number. So you can see the effect of current number also here. So if I put 1, I'm going to get like this. So this wave is moving in the x direction. So you can see everything is perfect. Okay, so if I close this and go to again Lax scheme 1, and the current number, if I take 0.5, now you can see. Okay, so there is a diffusion error is coming here. And you can see in the dissipative error, there is the amplitude gets decreased and here it gets rounded off. And so you can, if I take some same scheme with 0.25 as the current number. So now there is more decrease here and there is more diffusion here. And I am getting more waves because when I am reducing current number means delta T is reduced. So I will have more number of waves the iterations for a given time period. So that's why there are more curves here. That's all. So this is lax scheme. And if I give 2, I'm going to get lax Van And again, I'm giving 1 here. So again, 1, it is coming perfect. And if I give 2, lax Van 0.5 as a current number. So you can see here, now some dispersion error is added here. Because lax Van is the second order scheme, and the derivative, third order derivative will be there in the error. And if I take again 2 with 0.25, so here there will be a little bit more here. Okay, so that is the way it will be. So then like that we can check all these schemes. Okay, upwind explicit 3 and number 1. So upwind explicit is upwind means only first order accurate in space. So we have dissipation error. So you can see dissipation error here. And again, if I give 3 and some 0.5, okay, so there will be more decrease in the amplitude. So like that you will have. And suppose if I take McCormack or Crank-Nicholson 4, number 1. So even for C equal to 1 also, the current the Crank-Nicholson is there, dispersion error is there, you can see. And if I take 4 and 0.5, and actually because it is an implicit scheme, I can take large current number. Okay, so if I take 4 and current number I take 2. So you can see, because normally implicit scheme means I am tempted to take large delta t. So when I take large delta t, the oscillations will increase. As I told, we have to add implicit damping such cases. And if I increase further, suppose if I increase 4 and 3, if I give, now you can see it's completely off. So such things may happen. So in that way, you can, so this is the method, right? So you can see the solution of that. This is what I wanted to just demonstrate. Okay, I have to put. Now we'll see viscous Burgers solver. So Burgers equation, and but it is, I think I have to put some linear. Okay. Okay. So what I mean by that is Burgers equation. If I take, so it is ut plus ux is equal to nu ux x. Okay, this is Burgers equation, and this is non-linear. So if it is, if I take ut plus ux is equal to nu uxx, this is linear Burgers. Like this. If you take it inviscid linear, this becomes wave equation, like here ut plus ux is equal to 0. This becomes first order wave equation. So these are all special cases for the Burgers equation. So we are going to solve this particular one today. Okay, so this is the equation we take. And And same old methods we use. Just and this is still generalized, nonlinear general viscous like that, dou u by dou t into alpha plus beta u dou u by dou x. So linear viscous, this is the one which we are going to discuss. Nonlinear viscous, it will be u dou u by dou x. So it depends the values of alpha and beta. If beta equal to 0 and alpha equal to a, this becomes this equation. If beta equal to 1 and alpha equal to 0, this is going to become this equation. And when I have this type of equation, I have to write this nonlinear term as dou e by dou x, and e is equal to u square by 2, like we have done for nonlinear hyperbolic equation. In that way, we have to change this. Okay, and 2D equation, if you have, this is the term we will get, dou square u by dou x square, dou square u by dou y square, and here u dou u by dou x plus v dou u by dou y. This is a general 2D Burgers equation. And so I will have two equations. And this is in non-conservative form, u dou u by dou x, v dou u by dou y. If I have dou of u square by 2 dou x and dou of ub by dou y, this is conservative. Using, we have discussed that we have, if you add continuity equation by multiplying by u and add to this, I'm going to get this equation. And if I multiply by v to the continuity equation and add to this, I'm going to get conservative form for the v equation. So in that way, I'll get the conservative and non-conservative forms. Okay, in vector form also I can write. So if I write this 2D equation, this can be written in vector form because here there are two time derivatives, two x derivatives, two y derivatives here. So all these things can be written in vector form like this. So u and v, solution vector is uv. So that can be taken as q. So dou q by dou t plus dou e by dou x. So dou e by dou x is u square and uv. And dou f by dou y, f is uv and v square. Nu dou square q by dou x square, dou square q by dou y square. If q is u, I am going to get u momentum, x momentum equation. If q is v, I am going to get y momentum equation. So in that way, I can write in the vector form because later we are going to use this vector form also. Okay, now the all known methods we will discuss. Okay, FTCS explicit scheme. If I want to use FTCS explicit scheme, so I am going to use ui n plus 1, okay, at in. So ui n plus 1 minus ui n by delta t plus a. So central difference for this ui plus 1 minus ui minus 1 n by 2 delta x is equal to nu. For this central difference ui plus 1 minus 2 ui plus ui minus 1, because it is explicit, everything will be n by delta x whole square. Okay, this is the FTCS method. And if you take order of accuracy, delta t and delta x whole square. And stability, because it is explicit, it is conditionally stable. So we have discussed that because of this term, we will have c less than or equal to 1. And because of the diffusion term, we are going to get d less than or equal to half. And whenever these two are there, we will have the third condition. Actually, these two conditions will result into this also. These two also sufficient. The Searle-Reynolds number should be less than or equal to 2 by c. This is more restriction. So if this is satisfied, automatically these two get satisfied. Okay, so this is a FTCS method. But as we have seen that if it is inviscid, okay, if it is inviscid, this will not be there, and this will become first order wave equation. And we have seen that Euler's FTCS method is unstable, so it will not work, right? So then there is a problem. So FTCS works for some problems, but sometimes it gives problem when there is convection dominance is there. So because of that, instead of going for FTCS, we go for what is called as FTBCS explicit. What is FTBCS?
Like first step we do backward space and then we do central space.
Right. Thank you. So this we do backward difference and this we do central difference. So forward time, backward and central space explicit. So UI, again, this is at I and n, UI n plus 1 minus UI n by delta t plus a UI minus UI minus 1. This is backward difference at n by delta x. This is equal to right side the same thing. UI plus 1 minus 2 UI plus UI minus 1 by delta x whole square. So when you take like this, when you take order of accuracy, order of delta t will be there, but delta x only will be there because here I am taking only first order accuracy. And condition for stability will be same. Conditional and c less than or equal to 1, b less than or equal to 1, or is c less than or equal to 2, like this. But only thing, because it is first order accurate, sometimes people try to have third order approximation for third order accuracy approximation for this. Okay, so what we get is FTCS, this is FTBCS. And so here, this is with third order accuracy. If I write dou u by dou x with third order accuracy, we get, okay, it is like split into two terms. So this is the way we get. This is third order accuracy. Okay, what is the problem? If I have actually here there is one more thing. If I have second order accuracy, it will become unstable sometimes. And also, if I have second order accuracy here, it may bring dispersion error. So that is one problem. And also, if viscous effects are less, then it will become like FTCS for wave equation and it will not work. So because of those reasons, if I am happy with FTBCS, it is okay. But if I want more accuracy, so I have to put third order accuracy here. So if I put third order accuracy here, it will bring diffusion error only. So it will not be a problem. Okay. So this is the with more that is FTBCS only, but with more order accuracy here. So it is first order in time, this is third order in space, and this is second order in space. So in effect, it will be second order in space will be there. And then we have Dufort-Frankel scheme. And Dufort-Frankel scheme, what we do? So this is central time, ui n plus 1 minus ui n minus 1 by 2 delta t. And this is a central space. So these two are central space. But here, what is the modification we do? We replace this UIN. Here, 2 UIN should be there. That is replaced by the average of old and new values. If you remember, Dufort-Frankel explicit scheme. So what we are doing is, we are going to replace UIN by average of UIN minus 1 and UIN plus 1. The 2 and 2 gets cancelled here. That's why it will come like this. Okay, so if I rewrite this in this explicit form, we will get like this. And here, if you remember, second order in time, second order in space, but this extra will come, delta t by delta x whole square also should tend to 0 because of the consistency check. Okay, so this is Dufort-Frankel scheme. It is everything we have already discussed, so it is easy to remember. And then McCormack explicit scheme. So McCormack, again, if you remember, so this ui star is equal to uin minus, here we take backward difference, ui plus 1 minus uin by, and here this is central difference only. That is convection, we take backward difference here. And in the next step, I take, sorry, this is forward difference. In the next step, we take backward difference, ui minus 1. But I put star values here. That is, these intermediate values I have to use here. Okay, so this is the way we have to do the McCormack explicit. So because it is same concept, I am not discussing much here. And similarly, we have BTCS implicit. So BTCS implicit and FTCS explicit, what is the difference? We have to write all n plus 1s here instead of n's. Okay, so this is the way we get. And again, if I do BTCS implicit, I am going to get three unknowns, ui minus 1, ui, and ui plus 1. So if I write in this way, we are going to get, these are the coefficients for the tridiagonal matrix. C by 2 plus d, C by 2 minus d, this is 1 plus 2d. So if you see, if you add these two, it is going to be 2d. Sorry, not 2d. It is 2c, 1 half c.
1 plus C, sir. No. 1 plus. Okay, okay. Uh, yeah, it's 1 plus C, sir.
2d, I think it will come. No, not like that. This d minus d minus. So it will be 2d. If you take modulus of these two, c by 2 gets cancelled. So minus d minus 2d. So modulus, if you take 2d, it will be. And the diagonal term will be 1 plus 2d, more than the sum of these two. So that is the way we get the diagonal dominance. Okay, so this is BTCS implicit scheme. And similar to BTCS, you can have BTBCS implicit. Okay, so backward time, backward and central space. Okay, so this is backward in time, and this is backward in space, ui minus 1. Why? Because BTCS, again, it may give some problem sometimes, because it is if it is convection dominant, it will not depend on the downstream value, it depends on the upstream value. So BTBCS behaves well. So this is taken. So here again, this is first order accuracy. And because of this, again, if you want to have third order accuracy here, again, you will write like this, just as we have discussed in FTBCS. Okay, so this is the way we can have BTBCS implicit scheme. Okay, an application problem is done here. And so this, the solution of this particular equation, the solution of this equation, analytical solution is given here. This is the analytical solution for that. So what you are asked to do is, it is an exercise problem. Solve the viscous Burgess equation by the following schemes: FTCS explicit, McCormack explicit, BTCS implicit. The domain of interest is -9 to 9. Okay, the boundary, that is the domain. And the initial distribution of U is given as, this is the initial distribution. That is, actually, this is the solution. U equal to 2 sine hx cos hx minus e power minus t, which is U is a function of x and t. At any x and t, I should be in a position to get the value of U. So at 0.1 time, so this is taken as the initial distribution. And so based on that, I have to march in time, and I have to find out how the things will be, and I can, so that I can compare with analytical value. Okay, so that is the way. And so this is to be solved with different delta x sizes and delta t sizes. So use step sizes delta x equal to 0.2, delta equal to 0.01. Print and plot the solutions for all x locations at t equal to 0.1, 0.4, 0.7, and 1. To investigate the effect of step sizes and accuracy and stability, consider the following cases like this. So here, if you see the analytical solution, this is the way like this. At different times of 0.1, 0.4, 0.7, 0.1, right? Initial one is this. So as time progress, it is going to be almost like a step function, it will come. So initially it is like this, and as time progress, because of the mathematical behavior, it changes, the distribution changes, and gradually the amplitudes reduce here, and it becomes like almost like a step. Okay, this is the analytical solution. And so if you apply FTCS scheme, right? So I'm going to get this again for different things. So you can see that the domain is varying from -9 to 9. Okay, so delta x is given to be 0.2. So actually, how many points I will get total? 18 distance is there. 18 by 0.2, 90 points, I think, right? So 91 points will be there, 90 intervals will be there. Okay, that is the way it will be solved. I think I have program for this also. Just we will see. Budget solver, yeah. So lags and drop, upwind explicit, crank Nicholson, BTCS implicit. So all these schemes are used. Okay, this is the this is non-linear. Just I think this is the one. Yeah, FTCS, yeah. FTCS, FTBCS, Dufort-Frankel, McCormack, and BTBCS implicit. Okay, these schemes are used. And if you see, this is -9 to 9 with 0.2 interval. So I have X array like this. Okay, total length is 18 and dx is 0.2. So number of points will come length by dx plus 1. So here dt is 0.01. And so initial distribution, so I'm going to get like this. Here exponent e power minus 0.1. So that is the initial distribution. So then I have to use different schemes. So for one FTCS explicit scheme, so this is, you can see, ui is equal to c by 2 ui plus 1 minus ui minus 1. That is which we have written. So if I so here this is written as uin plus 1 is equal to uin plus c by 2 a delta t by delta x b c by 2 into ui plus 1 minus ui minus 1, and this is minus, right, because it goes to the right side, plus d into this, all these things will be there, ui plus 1 minus 2 ui plus ui minus 1. So this is to be seen in that program. So you can see ui minus c by 2 into ui plus 1 plus u minus ui minus 1 plus d into ui plus 1 minus 2 ui plus ui minus 1. So that is the way we do. This is the only line, okay? And then it is for second thing, second scheme is Dufort, FTBCS explicit scheme. So FTBCS, you can see here c into ui minus 1. Okay, so backward difference. I have used only first order accurate, third order accurate I didn't write. Okay, so like this, I can write for all the schemes. And if I execute, so 1. So you can see this is the way we get. Okay, and if I give to and 3, so I think this is taking small value and everywhere only one time step or something it is taking. This is 4 is a McCormack explicit. Why it is coming like this? Maybe I have to check that. Okay, we'll see. 5 is the BTCS implicit. 6. So this is BTDCH implicit. Only McCormack, I think there is some problem. I don't know. I have to check my program. This is U star minus C into UI plus 1 minus UI plus D into UI plus 1 to UI. So maybe just I have to check this formula. So all things will work well. So that is the way the budget solver is used. Okay, this is about budget solver. I think, okay, one more important thing I have to do. I will do the stability analysis. Okay, we'll take FTCS. I will have UI in plus 1 minus UIN is equal to minus C by 2 UI plus 1 minus UI minus 1 plus D into so this is the way I have, and using von Neumann stability analysis. Okay, so what will I get? Can you tell me? Here e power a delta t I will get, minus 1 I will get is equal to minus C by 2. Here, can you tell me what is that I will get? UI plus 1.
E power ikmx.
I theta I will put minus e power
Minus I theta.
minus I theta plus D into
Same again, e power I theta.
I theta minus 2 plus e power minus I theta. Like this I will get. So e power a delta t is equal to 1 minus C by 2 into what is that I will get here?
2 cos theta.
2
No.
2 I sin theta.
2 I sin theta. Yeah.
2 I sin theta plus D into 2 cos theta minus 2.
Minus 2.
Like this I'll get. So this 2 gets cancelled. So this can be written as 2D into cos theta minus 1. Okay, so this is 1 minus 1 plus 2D minus 2D cos theta minus IC sin theta. This is Z I will get. Okay, real and imaginary values. So this is complex. So what I have to show is
G bar less than 1.
or G bar should be less than or equal to 1. This is the way I have to put. So G bar is equal to real square plus imaginary square. So 1 plus 2D minus 2D cos theta whole square plus C square sin square theta, like this. This I have to do. So this is equal to, if I take this as A and this is B, A minus B whole square. So 1 plus 2D whole square minus 4D into 1 plus 2D cos theta plus 4D square cos square theta plus C square sin square theta. Like this I will get. This is equal to, so this if I write as C square into 1 minus cos square theta, okay, and so I will have 4D square minus C square cos square theta Okay, so this cos square theta and this cos square theta I am written, and minus 4d into 1 plus 2d cos theta. So cos theta terms, cos square theta terms are over, and the remaining constant terms plus
Plus c square sin square theta.
no, c square sin square theta I am writing as
Oh,
c
sorry.
square into 1 minus cos
Then
square.
only 1 plus 2d whole square is
T
remaining.
square will be there, and 1 plus 2d whole square, that is 4d square plus 4d plus 1 plus c square. Okay, I think this is the way I will get. Okay, so I got some value. Here, it is a little bit complicated to show how it is. So what we do is, we take the extreme values of cos theta. Cos theta can be plus 1 or minus 1. Okay, so for these two values, I will check. Okay, so if cos theta is equal to plus 1, so I will have, so 4d square minus c square minus 4d into 1 plus 2d. Plus 4d square plus 4d plus c square plus 1. Something like this. Okay, so this is so if I see this, actually here 4d square 8d square, and minus 4d into 2d 8d square gets cancelled. So this c square also gets cancelled. Here minus 4d plus 4d also gets cancelled. Everything you will get only 1.
Yes, sir.
So g bar is equal to 1. So no problem of stability. If cos theta is equal to 1. So if cos theta equal to minus 1, so what will I get? So cos square theta, no problem. It will be 4d square minus c square only, the coefficient of cos square theta. But this is coefficient of cos theta. It will become plus 4d into 1 plus 2d. The remaining things as it is, 4d square plus 4d plus c square plus 1, something like this I will get. So here, if I just simplify, this minus c square plus c square goes off. So I will have 4d square plus 4d plus 8d
8d
square
square.
plus 4d square plus 4d plus 1. Okay. So 4d square, this is 16d square plus 8d less than or equal to 0. This way I will get. This is
When d is negative or like, yeah.
16d square here would be,
It's correct, sir. It's correct.
okay, 8d into 2d plus 1. In minus 1 or plus 1 here, there is some problem. I think somewhere I have done some mistake. Minus 4d into 1 plus 2d. So this will be 4d into 1 plus 2d.
Sir, in the end, no, sir, everything is looking fine only, sir.
There is something on this.
Like, is GG bar correct, sir, in the textbook?
Yeah, GG bar is okay. That's okay. Oh, okay, that expression, huh?
Yes, sir, expression, sir.
Expression GG bar 4d square minus c square plus 4d. This is plus 4d into 1 minus 2d. Just we'll see here. Plus 2d minus 2d cos theta plus 2d. Okay, here actually there is a plus 2d cos theta will come. Here, if you see here, 2d into cos theta minus 1. So minus.
And minus 2D also, sir, I guess.
No. This and this should have opposite signs.
Sir, it is 1 minus 2d plus 2d cos theta.
Yeah.
Yes, sir, yes, sir.
So 1 minus 2d plus 2d cos theta. Okay, so this will become 1 minus 2d. So this will become actually 4d plus 1 plus 2, 4d into 1 plus 2d. Okay, when cos theta is 1, no problem. When cos theta equal to minus 1, it will become actually, this will become 8d into 2d minus 1 you will get. Okay, so just you can check, okay, and 2d minus 1 should be less than or equal to 0, or 2d less than or equal to 1, or d less than or equal to half. Okay, this is one expression I will get like this. And another thing, so if I write GG bar is equal to okay, this actually will okay, so like this we got. And here, because GG bar is a function of cos theta, so if I draw a line or a curve for GG bar and cos theta, so I will get a curve. And so this curve, if I see, it should be less than the minimum value of that. So to get where the GG bar is minimum, so I have to do the derivative of dGG bar by d cos theta. And if I take the second derivative, that should be greater than or equal to 1. Okay, so like that if I do, so what I'm going to get is 4d square minus c square 2 cos theta plus 4d into 1 minus 2d, like this. And if I take d square gg bar by d cos theta whole square, so I'm going to get some 4d square minus c square into 2 should be greater than or equal to 0, like this. So it comes like 4d square minus c square greater than or equal to 0, or 4d square greater than or equal to c square, or c square less than or equal to 4d square, or c less than or equal to 2d. And if you take d should be d as equal to half, okay, the limit, so it will come to c less than or equal to 1. Okay, something like this, we get the other one, c less than or equal to 1. Okay, and so what he says is the more restrictive requirement it is like because c square it is 1, 2d, this is also if the limit is 1, and c square should be less than or equal to 2d. So this is a little bit more restricted requirement we get. So here what he does is C by D, 1C I will keep here, 1C I will take to this, 2 by C. So C by D, A is A delta T by delta X into D is mu delta T by delta X whole square. So less than or equal to 2 by C, and delta T if I cancel, delta X if I cancel. So I'm going to get there A delta X by mu less than or equal to 2 by C, or REC less than or equal to 2 by C, I guess. Okay, this is the way I get. So actually, if I satisfy this, and any two of them will give the third one. So I need not write all the three, but if any two of them, if this is a more restricted requirement. If this is satisfied and one of them is satisfied, the other one automatically gets satisfied. Okay, so that is the way the cell Reynolds number comes. As I told, because this is velocity and this is distance and this is the viscosity, so I'm going to get similar to a Reynolds number. Okay, this is about the stability of the Burgess FTCS. Okay, this is what I wanted to do. And okay, as far as the exams are concerned, you have to be good at finding out the stability and consistency. Whatever I have told, only few I have proved, but I may ask some other scheme to check the consistency or stability or error analysis. So you have to know the concepts and be clear about how to do about it. Okay.
Okay.
And so I'll go to the story. It's a very simple, touching story. Okay, in a telephonic interview, the radio announcer asked his guest, a millionaire, "What made you happiest in life?" The millionaire replied, "I have gone through 4 stages of happiness in my life. Finally, I understood the meaning of true happiness." The first stage was to accumulate wealth and means. Okay, that's what all people from the childhood, the main aim of every person is to have highest package. Okay, so now for all of you, that is the main goal, to have the best package. Right, you studied hard in +2, you tried to enter into NIT and into some best, first tried for computer science and then got into mechanical. So all these things happen only because you want a big package. That is the goal from the childhood, right? You are driven to that by your parents, by your peers, by your college or institutes and all these things. Okay, so the first stage was to accumulate wealth and means, but at this stage I did not get the happiness I wanted. So because he became millionaire, now there is no problem for that, but he didn't find happiness in that. Okay, then came the second stage of collecting valuables and items. Okay, money will not give you happiness, but the use of money is to have valuables. Okay, so he started collecting valuables and items. But I realized that the effect of this is also temporary, and the luster of valuable things does not last long. And then came the third stage of getting big projects like buying a football team, buying a tourist resort, etc. But even here, I did not get the happiness I had imagined. And the fourth time, a friend of mine asked me to buy wheelchairs for disabled children. At the friend's request, I immediately bought some wheelchairs. because it is just money. He thought he can fulfill it. But my friend insisted that I go with him and hand over the wheelchairs to the children myself. So I went with him and gave the wheelchairs to those children with my own hands. I saw the great glow of happiness on the faces of those children. I saw them all sitting on the chairs, moving around and having fun. It was as if they had arrived at a picnic. But I felt real joy when I started to leave and one of the kids grabbed my leg. I greatly tried to free my leg, but the child stared at my face and held my leg tightly. I bent down and asked the child, "Do you need anything else?" The answer the child gave me not only made me happy, but also changed my life forever. The child said, "I want to remember your face so that when I meet you in heaven, I will be able to recognize you and thank you once again." Thank you. Okay, thank you. All the best.
Thank you.
Thank you, sir.
Thank you.
Sir, this is the last class, no, sir, before meets.
Yeah, before mid, I think this is the last class.
Yes, sir. We'll meet again on March 2nd, sir.
Yeah. What about Monday? Is it classes cancelled or anything like that?
Sir, I think the purpose of not having an exam on Monday is for the Technosian event, sir.
That is
And if we have again classes, there is no point in having